Okay, so time to get started. Here we were last time. We were talking about dot products. I mean, super briefly. We ran out of time. So picking up where we left off. I mean, again, so remember this is a review thing. Don't forget that's the formula. There's a bunch of properties in the book. Cultural note. It's the model for the idea of inner products. That's pretty cool. And then, there's this little bit here. This is it's a pet peeve of mine, right? This is not something you need to worry too much about, but it really is silly if you really think about it to have two words for two distinct ideas that happen to have a lot of overlap. Okay, yeah, sure. But distinct ideas, two words, two ideas, we really ought to pair them up and make sure to keep the distinction, right? So I think that the choice should be that perpendicular refers to a geometric statement about directions, right, which don't exist for the zero vector, right? And orthogonal is this algebraic statement about dot product being zero, right? And so again, yeah, a lot of overlap, right? But important distinction. Okay. All right, so picking up from there, a really quickie theorem. If you have a non-zero vector, and if you are interested in the unique vector, the unique unit vector that points in the same direction. And by the way, this comes up a lot. Very often we need to know what is this unique unit vector pointing in the direction of a given vector. Well, there's the formula. And all you have to do is take the original vector you were given and divide by its own magnitude. End of the business. It's that easy, right? Very simple little formula. So make sure that you're comfortable with this formula. It's a nice little exercise to think about why this is true. See if you can write down the argument. But anyway, most importantly, make sure you know that is true and know that formula. Component is an interesting idea. This is something we'll have use for. Used a lot in physics and engineering. So the idea of a component is that you have some vector that you're interested in. And, okay, yeah, that vector is interesting, but it's only interesting, let's say, because I'm interested in to what extent it points in that direction. Let me do a better job with there we go. Easy little silly example. Let's suppose you're playing football, right, and the ball starts here, and then you get tackled here. How many yards gain is that? Well, it doesn't really matter. The actual distance that the ball moved, you only care about the extent to which the ball moved downfield. Right? So that's an example of a component. Importantly, notice that the component, as I have indicated here, can be negative. Right? You can lose yards in football. Right? It's not a distance, it's a scalar. And another little subtle important distinction, a lot of people think of distances and coordinates as being kind of the same thing. Like the x-coordinate is basically a distance. If it's positive, yes, but very importantly, distances are never negative. Coordinates, of course, can be negative. Right? So this is really more like a coordinate than it is like a distance. Okay, so how do we get our hands on this? Well, we would need to talk about the direction in some specific terms. Very often, usually I'll say there is another vector that we use to indicate the direction about which we care about W. Right? So some vector V that defines the direction we're talking about. Okay, and so how do we compute the component? And the big idea is to just notice that this is a right triangle. The component that we're interested in is, okay, now forgive me, I'm going to commit a little math crime here. It's the length of one side of the triangle. It's not actually a length, it's a coordinate. It could be negative, so again, shame on me for saying that, right? But for intuition, sort of convenience of computation purposes, for the moment, we can think of it as being a side of the triangle, and trig is something that y'all are all good at, right? So there you go. You write down the trig of that triangle. and do a little algebra with it, and out comes this nice result that we have a very convenient formula for how to compute components. It's this formula right here. Details in the algebra, y'all can check that, of course. Okay. All right, so now this is a fine formula, I suppose, but here's a version that I like better, and that is to notice, you can see it right here, that right there is v divided by its own magnitude. That right there is the unit vector pointing in the direction of v, right? So it's arisen naturally. Didn't really even see that coming, right? But it arose very naturally. And so, yes, you can think of the formula as w dot the direction vector divided by the magnitude of the direction vector, but that's doesn't really roll off the tongue so well. You know, that's kind of clunky. I think it's much more natural just to rewrite it as component is dot product with a unit vector. Much simpler. And this actually, I think, really does roll off the tongue very nicely, and that's what I have right here. So components are dot products with unit vectors. Nice and pithy. Right, so nice application of dot product, nice application of the idea of a unit vector. How we doing? All right, related idea. Now let me go back up here before I move along. Reminder, the component, right, is a coordinate kind of thing. It's a scalar in particular. It can be negative, it can be positive, right? But it's a scalar. It's not a vector. It's a yardage gained or lost, if you like the football metaphor. Okay, related idea, but importantly different, is the idea of a projection. So a projection of a vector in a given direction. So, in the same kind of starting setup. We got some vector, we got some direction about which we're interested in it. And now this time, you see it, we're looking at the same side of the triangle, kind of. Very, very similar little setup. Big difference, though, this thing that we're talking about now, what we're going to call the projection, is the vector. You might say represented by that side of the triangle, not the scalar, the vector. Right now, so how are we going to get our hands on that? And there's different takes you can entertain on how to think about this. I'm going to show you my favorite take. I think this is the most natural, ultimately conceptually natural way to think about it, and that is that look, this vector has two features, like all vectors do. It has a direction and it has a magnitude. And good news, I know how to write those down. Right? So here's the unit vector that represents the direction, and I just multiply that unit vector times the magnitude, and now again I'm committing a little math crime. Yes, it could be negative. Magnitudes can't be, right? So, but again, it works out. The magnitude, what I'm going to loosely call the magnitude, is the component, which of course is computed with the dot product with the unit vector. Now, I consider this to be a really easy argument to remember, because it's just a recognition that we kind of already knew the answer. We're looking for a vector. Vectors are a unit direction times a magnitude, both of which I know. So, super easy to remember. This is the only formula for projection that's like permanently in my head. Right? This is what I consider to be the formula for projection. Okay, now let me show you a different formula for projection. It's equivalent. It's morally the same thing, really. It's just recognition of what happens when you take that unit vector and write it in terms of the original given vector v. That's all it is. We're just plugging that in. Okay? And if you kind of, again, work out the algebra, y'all are good at algebra, and see what you get, then you get instead this formula for projection. And now let's compare and contrast. See if I can fit these both onto the, here we go, both on the screen at the same time. Let's compare and contrast. Which of these is the better formula? Well, what I like about this one down here is that it's written entirely in terms of the two vectors that I'm given. It's written entirely in terms of the thing I want to take the projection of and the vector defining the direction in which I want to compute the projection. Right? So it's pluggy-chuggy convenient. There's something to be said for that. I'm not in favor of inconvenience. Right? So I do give it props for that. Here's what I don't like about this formula. It's not particularly transparent where it came from. Right? If you're sitting there on a test trying to remember, wait a minute, which way does it go? Is it, oh gosh, is it W dot V divided by W dot W, or is it V dot W divided by V dot V, or which way does it go? It's hard to remember. And you might think to yourself, yeah, I'll cram it right before the test, right? Okay, but what about 10 years from now? 10 years from now, you won't remember, right? But I'll bet you'll have trouble forgetting. If you really understand this idea here, you'll have trouble, even if you try, to forget this, because this is conceptually transparent. Direction and magnitude. Boom. Right? Very straightforward. Now, I'll remind you, as you decide, how you want to approach this. This is a course about ideas, right, and reasoning. It's not really a course about answers. This is not a plug and chug kind of a course, right? So the fact that this has a plug and chug advantage, small advantage, maybe a little bit, right? And I'll tell you what I would do if I were a student in this course. I would make sure to know both of them really comfortably, right? And then, yes, I would also cram this formula right before the test. Sure I would, right? But the idea that this is an alternative to that, I think, is a huge mistake. Again, you're going to need concepts as we go forward in this class, and this is the one that's most conceptually natural. Okay, for your consideration. All right, last little quickie comment before we go on to 1.4. The book has various, I think, couple of examples anyway of showing how you can use vector algebra to do proofs in plane geometry. There's some pretty cool little arguments there that they can't show you in high school geometry classes because you don't know what a vector is at that stage. Well, in most cases, all exceptions granted. So anyway, various facts of plane geometry that are otherwise inconvenient to prove are easy if you set up the question in a complete and natural way, and then just use a little vector algebra. So it'd be worth your time to look at those examples. Looks like there are two nice examples in the book, and I think there's at least one homework exercise that's kind of in the same direction. Same basic idea. All right. Okay, cross product. So now, cross product. I'm going to confess one thing right off the bat. This is a topic where what I would like to say and what I can really justify spending time saying, again, in a class where, we have to make tough choices, a lot of content to cover and stuff, and where there's really the greatest gap here. And so when I wrote these notes, I wrote them with optimism, right? And sure that I would have time to say all these things, and it's just turned out that I just don't, right? Now, the things that I have begrudgingly accepted that I have to not say in class are also things that are non-trivial ideas. And so I'm not going to say that what I skip here is stuff that you should read, stuff that you're responsible for reading on your own. I'm going to say you're actually not responsible for some of this stuff. And I'll be very explicit as we go through. And it's unfortunate, and wish we had more time, that we just don't. Okay. But it remains the stuff that's in here that you are not responsible for, that you do not have to read. It's still pretty cool. It's still conceptually instructive. It still might help you understand the rest of the stuff. I'm not saying you shouldn't read it. I'm saying you don't have to So decide for yourselves. Okay. All right, so we're going to start off some introductory ideas, what I'm going to call the geometric order of a list. We'll start off with the idea of a list. Here is a list. A list has an order to it. Right? So the first one that's written is the first vector in the list. The second one written is the second vector. The order that they are written down matters. A comma B is not the same as B comma A as a list. So very importantly, we're not talking about a set. We're talking about a list. The order matters. Okay, so when you have a list, I make the observation that you can define what we call the geometric order, which is going to be one of these three ideas here, by kind of looking at the picture. And so in particular, the first vector, let's highlight the first vector in the list, A. Right? And then we also have a second vector in the list, B. And notice that if you look at that list where A is first, B is second, and if you think about which direction are we rotating, starting in the direction of A, ending in the direction of B, well, if this is what those vectors are, then that is a counterclockwise list because, check it out, right there in the picture, rotating from the A direction to the B direction is counterclockwise. Now, on the other hand, a different geometry, different list, a different collection of vectors, A and B. If A were that and B were that, as drawn here, well, that would be, again, A first, B second. A first, B second. Notice I rotate clockwise. Right, so this is kind of an interesting idea. It's not particularly deep. The way I'm presenting it here. Oh, I should recognize sometimes it's neither. Right? Which way do you rotate from A's direction to get into B's direction? You don't move at all. It's neither clockwise nor counterclockwise. Likewise, if A pointed exactly opposite. Likewise, if A was the zero vector. Likewise, if B was the zero vector. Likewise, if they were both zero. There's various different versions of this, all of which, you'll notice quickly, are linearly dependent. So this is kind of the three different cases. If when you have two vectors in R2, that list is either counterclockwise, clockwise, or dependent. And why are we talking about this? I'll reveal later. But there's some nice observations to be made about the geometric properties of these ideas. Here we go. Let's see here if I can, so counterclockwise and clockwise are mirror images of each other. Right? You look at a mirror, at a clock, it's going the wrong way. Okay? If you switch the order of the vectors in the list, that will switch the order of the list. So A comma B is counterclockwise. Those same vectors, but writing B comma A becomes clockwise. This is not deep, right? This is just kind of observations about these very familiar ideas. And then likewise, it's independent of rotations. So if you look at a clock, so there's a clock on the board right back there. I'm looking at the clock. I'm watching which direction the hands are going. If I turn my head to the side like that, yep, still going the same direction. So rotating both vectors doesn't do anything. All right. Now this is a lovely segue into a more sophisticated idea. And that is, what is the analogous version of this if I have three vectors in three dimensions? Is there a clockwise, counterclockwise kind of concept there, right? Well, yes, there is. It's based on human hands. Well, there's different ways to think about it. The easiest, I think, way to think about it is based on human hands. I'm going to start with what's, what would it mean for this list to be right-handed. Keep in mind the order matters. A is first. B is second. C is third. That matters. And here's the way we do it. There is a particular hand gesture that got settled and agreed upon long ago. I don't even know how long ago. This is the hand gesture right here. The rule for this hand gesture is that the index finger points parallel to the palm. And don't get clever by bending your finger around in different ways, right? Index finger parallel to the palm. The middle finger bending the way fingers want to bend. Again, don't get clever and cute with this move right here, right? So index finger parallel to the palm, middle finger bending the direction it wants to bend, and then thumbs doing what thumbs want to do. Please don't. This is not allowed, right? So nice, simple hand gesture like this. And the index finger is first. Arbitrary but standardized rule. The index finger is first, the middle finger is second, the thumb is third. First, second, third. Right? And so the idea is, can you arrange your right hand to represent the vectors in question? And I think you can see if you look at this first, what I have labeled as right-handed there, right? I've got my index finger, first finger, pointing in the direction of the first vector, my middle finger pointing in the direction of the second vector, thumb and kind of in the direction of the third vector. So that's right-handed. And if I try to do that with my left hand, I will fail. Let's see, how would I even, let's see here, I guess I would have to do it like this. Okay, I can point my index finger in that A direction. But how am I going to get my middle finger to point in the B direction? I would have to do this. And now check it out, my thumb's going the wrong way. Everybody see that? Okay. So it turns out that this is basically a three-dimensional version of clockwise counterclockwise. So we have a right-handed list, as we've just discussed. By the way, notice this list here is left-handed. Right? A, B, C. A first, B second, C third. Check it out. With my left hand, it works just fine. Yeah. By the way, just a finer point. The first two vectors define a plane. And when you think about the role that the thumb plays, all you really need to recognize is that third vector in the list points on one side of the plane as opposed to the other side of the plane. And don't worry about whether you can actually maneuver your thumb exactly in the direction of that third vector. The question is just, does your thumb point on the same side of the plane as the third vector? And if it's on the same side of the plane, then yeah, that's good enough. Okay. All right, and again, counterexamples, right? Various different sort of, here's a trio of vectors where it just doesn't work left-handed or right-handed. And again, various different versions, and you will note that they are all linearly dependent. Okay, and again, we get all these same properties. If I can get this to cooperate. Right hands and left hands are mirror images of each other. Right? If you trade the positions of two of the vectors, the geometric order changes. Now this one you really have to think through. Now let's start with this list here, A, B, C. A first, B second, C third. It's clearly right-handed. Right? You look at the picture, look at my right hand. ABC is right-handed. But now let's think for a moment. What if I change the order of the vectors in the list? What if I do B, A, C? I can't make B, A, C work. I can make the B and the A work, but then my thumb's not pointing in the right direction. Right? But B, A, C is left-handed. Everybody on board with that? All right. So, and then again, independent of rotations, right? So if I'm looking at my right hand and if I turn my head to the side, it still looks like a right hand. So not a deep point. So I think it's really interesting to observe that right-handed and left-handed splits up lists into two sort of opposite states, and then the one in between that's kind of the anomalous kind of annoying intermediary case. And the three properties are just like the resulting three properties for right hand, left hand. So I think a very strong case could be made that this business about right hand order and left hand order is just a three-dimensional version of clockwise counterclockwise. All right. Oh, there is a fourth property that there isn't even really an analogous question that we can ask when we're talking about two vectors in two dimensions. What I'm going to call cycling the list. Cycling the list means that I kind of keep pushing them over until I get to the edge where it falls off, and then I kind of come back around to the other side. So just kind of, everything shifts over, and then the one that falls off goes back around to the empty space at the end. That'll always preserve the geometric order. And let's see if I can get this right now. The geometric sort of intuition behind why that works. I'm just going to do the hand gesture. This is it right here. You see this little move I'm doing with my hands? Right? So this is effectively the geometric version of cycling. And of course, it's a right hand. It's still a right hand. So the order is preserved. Yeah?
What's the difference between cycling and rotation?
Because I'm literally changing the list here. Right? That's changing the list, but not changing the vectors. Rotating says I'm going to change the vectors. Right? I'm not going to look at A anymore. I'm going to look at the rotation of A, et cetera, et cetera. But the order is effectively retained. Right? Yes.
Is there a reason we're not calling it negative and positive?
Yeah, absolutely. That's a great question. And that's because there's nothing really intrinsically positive or negative about either one. Right now, these two things do have something in common with the ideas of positive and negative, and that is they are opposites of each other. But positive and negative has more intrinsic structure, I'm going to say, because positive times positive is positive. Negative times negative is not negative, right? There's an asymmetry with positive and negative, and there isn't really here. These are just different. They're opposites of each other, and that's all. Does that make sense? Yeah. It's a great question, though. Yeah, absolutely. So we want to try to avoid attributing meaning to things that aren't actually there. Yeah. Yes.
Okay, so would we be given if it was right-handed or left-handed, or would we have to find it?
I'm just defining ideas right now.
Okay.
Yeah. So exactly how I'm going to test you on those ideas. There's a million different versions of that. Yeah. Okay. Yeah. All right. Okay. So So here's a couple of theorems that I'm going to say you may have seen. You really should have seen. I hope they showed you these facts in linear algebra. My strong suspicion is that they showed you some of this in linear algebra, but probably not all of this. So this probably look a little bit familiar. Now, before I get into the result, the punchline of the theorem, I've got to do a bunch of setup. There's a lot of setup in this question. So everything that you see up on the board here is not a theorem. This is just setup. We haven't actually gotten around to saying anything yet. So here's what we're going to talk about. We're going to talk about a list. Two vectors in R2. I point out that a list allows me to make a matrix. Now, how do I turn a list into a matrix? Well, I take the first vector in the list. I'm going to make that the first column in the matrix. I'm going to take the second vector in the list. I'm going to make that the second column of the matrix. Now, this is, again, our arbitrary choice, but this is, I'm going to call it natural. Right? So you give me a list, I can make a matrix in a natural way. Now, by the way, if you give me a matrix, I can make a linear transformation. Again, in a pretty natural way, right? And this is, again, the standard relationship between matrices and linear transformations. So, now, to be fair, again, I haven't really done anything yet. You gave me one thing, namely a list, and I have, from that, naturally kind of, I'm going to say canonically, two other mathematical objects. And now here is a fourth naturally created mathematical object, and that is this parallelogram. Specifically, the parallelogram that you get as a result of looking at the unit square, that's pretty natural, unit square, and applying the linear transformation to that unit square and see what you get. All right, so again, here we go. These are the four objects that we're going to discuss in this theorem. It all originates just from a list. We have a matrix, we have a transformation, we have a parallelogram. So here is the result. Some really cool, really shockingly, unexpectedly convenient results. The determinant of that matrix tells you loads of information. Yeah, the determinant of that matrix tells you geometric information about the list, it tells you geometric information about the parallelogram, and it tells you geometric information about the linear transformation itself. So in particular, the magnitude of the determinant tells you the area of that parallelogram. Show of hands, how many people saw that already? So, okay, most. Okay, that's cool. Anyway, neat fact, the absolute value of the determinant, absolute value is very important. Area is an intrinsically positive thing. Determinant is not. Determinant could totally be negative. About half the time, determinant's negative. So, absolute value of the determinant gives you the area. Quick observation I'll make. The original unit square had area equal to 1, so in fact, another way to say the area of this is by what factor did that linear transformation stretch areas? So this is an important distinction. The area of this thing over here is what I'm going to call a static thing. The parallelogram just sits there, right? Nothing ever happens. It just sits there, right? The linear transformation is an action. It's doing stuff. It's taking inputs and giving outputs. It's a process, right? So not only does the determinant's absolute value tell you about the static result, it tells you about the process of what that linear transformation is doing. That's a pretty cool fact. Okay, and then here's the other thing about determinant. We can talk about the sign of the determinant. So that's either positive or negative. And that tells me positive or negative tells me whether the list is counterclockwise or clockwise. How about that? That's pretty surprising if you really think about it, right? Normally you would think, how would I determine a relationship between directions? I would think I would have to actually draw those vectors and look at those directions and visually decide which way is it, clockwise or counterclockwise. Nope. Just compute the determinant. Positive means counterclockwise. Negative means clockwise. Purely algebraic computation giving us geometric information about the list. And 0 means neither. Now, there's also some things to say about, what does the sign of the determinant say about the linear transformation? This is a little bit subtle, but here's the way I like to think about it. And let me get rid of my highlighting here. Come here. There we go. Okay. So we've already talked about how the transformation takes the square to the parallelogram. I will point out that the first standard basis vector, of course, is what goes to the first vector in the list, which is A, which is that edge of the parallelogram. Then let's, of course, the second standard basis vector, right? Remember, the columns are the images of the standard basis vectors. Second standard basis vector goes to the second vector in the list. And now, geometrically, let's make the observation that green to blue is clearly counterclockwise there and also counterclockwise there. So the fact that this list as drawn, AB, the fact that this is counterclockwise also tells you something about what this linear transformation does. This linear transformation preserves the geometric order. Counterclockwise lists turn into counterclockwise lists. Right? And let's think about what kinds of transformations could actually do that. And I will point out that if what my transformation is to take the plane on the left and kind of stretch it out, yeah, that would preserve order. If what the transformation does is to take this and do like a shearing transformation, something kind of like that, you think about the geometry, it would preserve order. But if what my transformation does is to take the plane and kind of flip it over, right? If we were to do this move, if we were to flip it upside down, or said differently, if I were to reflect, then this wouldn't happen. Counterclockwise would turn into clockwise. Okay? So, in the same way that the determinant, by being positive or negative, is telling us whether the parallelogram is clockwise or counterclockwise, or whether the list is clockwise or counterclockwise, it's also telling us whether orders are preserved or whether orders are reversed. Which means it's also telling us whether the plane is being flipped upside down, aka reflected, possibly in conjunction with other things, or not. And I'm using the term inverted here as kind of a catch-all of all the different ways you might think of flipping things over, flipping or reflecting. So there's a lot of information there, and this business about how I'm gonna clean up my mess. The business about how determinant of the matrix tells me about the list, y'all may have seen before. What it tells me about the parallelogram, you may have seen before. But what I've just told you about the transformation, I'll bet you this is news to most of y'all. Right? And I think it's a really important point of view. Again, the distinction being because this is something happening. This is action. There's a beginning, a middle, and an end in this, right? This is not a movie. This is a still photo. This is a parallelogram that just sits there, right? So that changes the way that we can apply these interpretations in some powerful ways. Okay, so good news. There's a three-dimensional version of this. It's the exact same thing. Oh my gosh, it's totally the same thing. It's 3 vectors instead of 2. It's 3-dimensional instead of 2-dimensional. It's a 3x3 matrix instead of a 2x2 matrix. It is a parallelepiped instead of a parallelogram. But I mean, this is pretty much, it's analogous, or it is a strong analogy to basically the same idea. And again, in the usual way, a linear transformation. And the result is exactly what you would think. The magnitude of the determinant, the absolute value of the determinant, gives you the volume. AKA the factor by which the transformation is stretching volumes. Okay. And the sign, plus or minus, is telling you about whether your original list is thinking about the analogy, whether your original list is right-handed or left-handed, about whether your parallelogram, looking at those edges, right-handed or left-handed, and about whether your transformation, does it turn right hands into right hands? By the way, there's all rotations turn right hands into right hands, right? All stretches, all magnifications, all shearings turn right hands into right hands. But reflections turn right hands into left hands, right? So again, whether the sign is positive or negative tells you pretty cool information, not just about the parallelepiped, not just about the list, but also about the related linear transformation. So very cool theorem, and very powerful in a lot of ways. We're not going to prove these theorems, by the way. Like I didn't even write down the proof. I believe there is a proof in the book. I believe that proof is far more trouble than it's worth. I believe that there's actually a very natural way to approach this theorem. There's actually a really elegant way to prove this, which is not in the book, and which I'm not going to show you because it's got some sophistication that we don't really quite have in this class. So it's just a little bit above. But when there is a really good proof that's a little out of reach, I don't feel it necessary to then, all right, well then let's do the long, tedious, laborious, cryptic proof. I don't see the point in that, right? Take a few more math classes, and you'll be able to understand the what I consider to be the best, the natural way to prove this result. Okay. All right. Now, all that settled. Cool facts about the cross product. First of all, a definition. Here you go. This is the definition of the cross product that we denote by A cross B. Probably noted in your linear algebra class. This, by the way, as I'm defining it here, strictly and only applies to two vectors in R3. So very importantly, two vectors in R3. Now y'all recall from the homework exercises, a bunch of y'all have been asking me in office hours about that exercise about the generalized cross product. And that too is a very cool construction. But it is it's not what we call a binary product. What I have here is a product where you give me two things and out comes one thing. It's what we call a binary operation. Right? So the word product, I mean, we're accustomed to that word being a binary operation. You know what I mean? So the generalization when you have more vectors in higher dimensions is, we get into some subtleties of sort of language choices that, anyway. Okay, so two vectors in R3. And you can memorize this formula if you like. I never have in my entire life. I've used it a million times. Never memorized it, ever. And I encourage you not to memorize that formula because it's so much easier to memorize what I call here this symbolic shorthand. This is technically a crime, right? We talk about determinant of a matrix. Better be a matrix. There is no such thing as a determinant of a bicycle. It's not a thing. So is this thing a matrix? Well, let's take a careful look. A matrix is made up out of elements, and the elements are supposed to be scalars. That's not a scalar, that's a vector. Can you do that? Is that even legal? Well, kind of not really, right? So this is a bit of a bogus expression right here, right? But if you set that aside, if you ignore the fact that that's not technically a matrix, and so we therefore cannot technically talk about the determinant of it, if you just sweep all that under the rug and just kind of go through the usual motions of how you would compute the determinant, this is a healthy exercise that you should do. In fact, you will get exactly that expression right there. And again, healthy exercise, and I encourage y'all to just crank that out. Just kind of in the usual way, just go across the top row and play the game and write it down, and boom, that's what you'll get. As always, ask me in office hours if you have questions about that. Let's recognize that's a weird formula. Certainly what I have on the left here is a very weird formula. This one at least is kind of, there's something, it's kind of vaguely organized or something. That's kind of cool. But still seemingly arbitrary. Here's a really neat fact about this cross product, and that is that this cross product, defined by this expression here, which of course is computationally by that formula, if I were to dot it with some other three-dimensional vector, the result of dotting it with some other three-dimensional vector is that determinant right there, and that's a legit determinant, right? This is an actual matrix. Those entries are actual scalars, no problem. So how about that? That's interesting. This is actually a really powerful equation, really, really important equation. This is called the triple product expression. This expression here is cool for the following reason, many reasons, but here's the way I like to think about it. I already know cool stuff about determinants. I mean, really cool stuff. We have lots of geometric knowledge and intuition about determinants. I already know cool stuff about dot products. Right? In powerful geometric ways, we're all dot product experts. So I have an equation that relates what I want to understand with things that I already understand. And that's a foot in the door. That's an opportunity to draw conclusions about this based on your knowledge of what it's connected to. So this is useful for that reason. So now we get into a list of properties of the cross product, where I'm going to excuse you from responsibility for seeing why these things are true. But again, I encourage you to look at them to the extent that you are motivated. And again, it will be helpful. It is useful, but you're not responsible for it. So, very important fact you must know. You are responsible for this fact. The cross product is always orthogonal to both of the inputs. What you're not responsible for is why. And again, it hurts my heart to say that. Mathematicians are all about why and mathematical reasoning and stuff like that. And it was really neat too. This is an awesome argument, but we just don't have time to go through it. And again, tough choices. So this is one that you're not even responsible for, but I encourage you to look at it. So neat fact though, if you have two vectors and you want to find another vector that's orthogonal to both, wow, that's tricky. How would you otherwise do that as a non-trivial thing? Cross product, bam, does it. Okay. Another neat fact, very surprising theorem here. The triple product is preserved by cycling. So now notice, there's a temptation to look at this and think, oh yeah, yawn, it's like associativity or something. It's not. This is very importantly not an associativity. We are rotating the vectors in a list where there are two different operations. Notice, on the left, A here is not part of the cross product. But in this expression that it's equal to, A is part of the cross product. That's weird. Right? So when you cycle the list of vectors that, as you write them down like that, then the triple product is preserved. Neat property of cross products. Again, you're not responsible for why, but again, very cool arguments, and I hope you'll look at it. The magnitude of the cross product is the area of the related parallelogram. Very neat fact. Let me color code this. This cross product, its magnitude is equal to the area of the parallelogram defined by the two input vectors to that cross product. Weird. Right? Very important to know. Useful information. By the way, geometrically natural. Right? If you give me two vectors, the parallelogram that they define, very natural thing to want to talk about. And the cross product's magnitude always equaling that means that cross product has another sort of very natural property. Yeah.
Are there supposed to be double bars on the other side of the A comma B, or is it a different notation?
It's a different notation. I'm sorry. So I've seen this elsewhere, I'm pretty sure. But so you're talking about this double bar right there?
Yeah.
So that two parallel lines, I'm using that as a semantical sort of like, seemingly natural. Interpret the word parallel when you see that, right? And so this means parallelogram defined by these two vectors, right? And then you'll notice down here I have a similar thing. I have another sort of parallel, and here I listed three things. That's the parallelepiped defined by those three vectors. Yeah. So thank you for asking. I always forget to mention that. Again, you don't have to know why this is true. That said, this is my favorite proof in the whole section. It's really cool. It's very clever. It comes out of nowhere. It's it's almost random. You'll notice the proof starts with something that we're actually not even interested in. Right? This thing that we start with, this determinant right here, is neither of the objects we're in. But understanding this expression allows you to understand both of those, as it turns out. So give it a look if you're so inclined. And then there's two more. Oh, am I out of time? Oh, I'm out of time, aren't I? Okay, we will draw the line right here and pick up there on Monday. Hope you all have a good rest of your Friday. See you Monday.